Everyone thinks a clock just tells time. They're wrong. A pendulum clock asterisk makes asterisk time. It's a subtle but profound difference. A grandfather clock in a quiet hallway isn't just counting seconds, it's physically creating them, one precise swing at a time. This steady, rhythmic motion is the heart of its enduring accuracy, a testament to some truly elegant physics. We often take these familiar ticking guardians for granted, but beneath their polished wood and brass, a remarkable dance of gravity and inertia unfolds, orchestrated by a simple swinging weight. It's a marvel that kept the world running on schedule for centuries. The story of the pendulum clock begins, as many scientific breakthroughs do, with a curious mind observing the world. In the early 17th century, a young Galileo Galilei noticed something intriguing about a swinging lamp in a cathedral. He observed that no matter how wide the lamp's swing, whether it was a small arc or a large one, the time it took to complete a full back-and-forth motion seemed to remain constant. This wasn't just interesting, it was a potential game-changer for timekeeping. This principle, known as isochronism, meaning equal time, became the foundation. It meant a pendulum, once set in motion, could provide a consistent, reliable beat. But how do you harness that beat to turn gears and move hands? It took another brilliant mind, Christian Huygens, in 1656, to build the first truly accurate pendulum clock. He understood that Galileo's observation wasn't perfectly true for all swings, but it was close enough to revolutionize timekeeping. Huygens' genius was in designing the escapement mechanism. Imagine a tiny, intricate dance between the pendulum and the clock's gears. The escapement allows the pendulum to release the gear train one tiny step at a time. It's a two-way street. The swinging pendulum pushes a lever, which momentarily unlocks a gear, allowing it to advance by one tooth. In return, the gear gives the pendulum a tiny, gentle push-a-kick, just enough to counteract friction and keep it swinging. Without this subtle kick, the pendulum would eventually lose energy and stop. This elegant feedback loop is what makes the pendulum clock a self-sustaining timekeeper, constantly regulating itself. So, what exactly dictates the period of a pendulum, how long it takes for one full swing? Primarily, it's the length of the pendulum rod. A longer pendulum swings more slowly, a shorter one faster. The weight at the end, called the barb, plays a role too, but not in the way you might expect. A heavier barb doesn't make it swing faster or slower, but it does make the swing more stable and less affected by air resistance. Think of it this way: the pendulum is constantly falling under gravity, then rising against it. It converts gravitational potential energy into kinetic energy as it swings down, and then back into potential energy as it swings up. This continuous exchange of energy, guided by the constant pull of Earth's gravity, is what gives the pendulum its reliable rhythm. It's a tiny, localized dance with the fundamental forces of the universe. For centuries, pendulum clocks were the most accurate timekeepers available, driving scientific discovery, improving navigation, and standardizing daily life. They truly set the pace of the modern world. Of course, they aren't perfect. Temperature changes can slightly alter the length of the pendulum rod, affecting its accuracy. Even subtle changes in gravity, like moving a clock to a different altitude, can have an effect. Clockmakers developed ingenious solutions, like compensation pendulums made of different metals that expand and contract at opposing rates, keeping the effective length consistent despite temperature shifts. Today, we have atomic clocks that keep time with unfathomable precision, but the elegant physics of the pendulum clock remains foundational. Its steady tick-tock is a reminder of how simple observation can lead to profound understanding. So the next time you hear that comforting rhythm, remember, it's not just a sound. It's a tiny, perpetual motion machine, a testament to gravity, and a beautiful example of physics at play in our everyday lives, quietly making time, one swing at a time. Subscribe if you want to keep uncovering the surprising science hidden in plain sight, all around us.